Hello and welcome to this presentation. My name is Pooya Saremi. I am a doctoral researcher at Aalto University in Finland. Our research evaluates the applicability of limit state criteria to a novel K-joint in a slimfloor truss. In this presentation, I will first talk about the research background and goal of the study, then introduce the finite element model, its validation and verification of scaling. I will then describe the parametric studies on the effect of steel strength and its results. And in the end, conclusions and future research. The novel joint shown in this image has been designed and been in use in Finland. A joint is part of a steel truss that supports hollow core slabs. The upper chord is a WQ beam, the lower chord is a plate strip, and the braces are square hollow sections. The joint is also reinforced with a plate welded between the braces. In previous research on this joint, scaled down joint specimens were designed and tested at laboratory to study the behavior of the joint. The goal of this research is to define the limit criteria for the structural design of this specific joint. One of the criteria defined by the Eurocode is the 5% principal strain mentioned in the part 5 of Eurocode 3. The use of this criteria is extended to structures made of steels up to a 700. Our research question then became, how does material grade affect the applicability of this criterion to this specific joint design? I will now describe the finite element model. Solid 3D elements with quadratic formulation were used to mesh the geometry. Small details such as welds were also defined in the geometry. We used Rick's arc length solver to take into account post-buckling behavior. The symmetric half of the joint geometry was defined in the finite element model for computational efficiency. Hinged boundary conditions were assigned to brace ends, and the chord end was clamped. For validation of the FEM, the location of the actual hinges in the test setup were also considered, as shown in the top image. This is the experimental boundary condition. For the parametric studies, the hinges were simplified and were placed at the member ends, as shown in the bottom image. Tensile load was applied to one brace, and the other brace and the chord end were supported. Tensile tests were performed on the material used in the test specimens. Two-stage Ramberg-Osgood equation was fitted to the test results, and the fitted values were then used in the finite element models. 3 finite element models with different geometrical scales were tested. The full scale has the actual build dimensions typically used in construction. The theoretical scale has the exact dimensions received from the similitude calculations, but the exact dimensions could not be found in among the available cross-sections in the market. So we had to choose the closest available cross-sections, and we ended up with the experimental scale, which has dimensions that are slightly different from the theoretical scale. The model with experimental scale is the model that is validated against experimental results. For validation, we use force displacement curves received from the experiments and from the finite element models. The force values are received from the brace ends as marked with asterisks in the top right image. The displacement values are measured as the deformation between the locations marked with crosses in the same image. In the left figure, the curves with positive displacement values are results from tension braces, and the curves with negative displacement values are results from compressed braces. The curves with dashed lines are from finite element models, and the curves with solid lines are from experiments. two sets of specimens made of S420 and S700 were used for the validation of the finite element model. The criteria we used for validation were the overall shape of the curves, the slope of the proportional segment of the curves, the maximum force and its corresponding displacement value, and the shape of the unloading segment of the curves. Based on these criteria, we concluded the validity of the finite element models. The parametric studies were performed using the fullest scale finite element model. And we needed to transition from the small scale validated model to full scale finite element model. In doing so, we compared the results from the small scale and full scale model to observe any possible changes in the behavior of the joint model. In the left figure, we scaled up the numerical results of the scaled down finite element model. They are marked by number 3. And we compared them with the results from the full scale model marked by number 2. We observed that the maximum forces match very well, but the displacements have 12.5% difference. And we think that this difference is because the equation we used in the similitude calculations only took into account the cross-sectional capacity of the braces and not the buckling capacity of the braces. In the parametric studies, 5 steel grades were used as listed here. Nominal strength values for the steels were taken from the Eurocode. The stress strain curves for the tube material were created using double-stage Ramberg-Osgood equation. The stress strain curve for the plate materials were created using 4-stage multilinear curves. The force displacement curves and the strain contours are used to compare the results at 3 load levels: the yield load, the limit load where the 5% strain is reached, and the ultimate load. The location of the yield load is marked by red triangles in the force displacement curves on the left. And it shows that the joint response gradually becomes non-proportional before the full yielding of the brace cross-sections. The strain contours show that the yield load, once it is reached, the brace cross-sections yield close to the welds. The location of the limit load on the force displacement curves shows that the 5% strain is reached in the tension brace before the ultimate load is reached in either of the braces. White arrows in the right images show where the 5% strain is first reached. And the ratio of the limit strain to ultimate strain shows that while there is relatively large margin of safety for S235 and 460, the margin of safety for S690 is very small. At the ultimate load level, the joint made of S235 has a gradual failure due to material ductility. S355 and S550 have sudden failures due to brace buckling, and S690 has a pseudo-gradual failure due to numerical perfect plasticity, which is assumed by Abacus software beyond ultimate strain in the material model. But the recent experiments we performed on specimens made of S700 showed that the failure is the local buckling of the compressed brace. In conclusion, the use of the 5% strain limit for S235 and S355 is well justified. For S460 and S550, it leads to a reduced margin of safety. But for the joint made of S690, it may not lead to a safe design. So our future research will be looking into identifying a suitable strain limit criterion for this joint made of S690. And derive design equations for the load-bearing resistance of this drum. Thanks for your attention.